Hey everyone, welcome to this video. We will talk about self-attention. To start things off, context matters. So we have two sentences, both using the word fair. At the county fair, Judge Jamie is fair. In English, the word fair can be used to describe an event, such as a county fair or like a job fair, and to mean unbiased, such as Judge Jamie is fair. This could differ in other languages. To translate correctly, let's get the context right. In sequence to sequence, translation got better by using every word in the sentence. However, when translating, some words are more important for the translation than others. So to make sure we translate the word fair right into another language, the word county and the word judge have a lot of context and will make the translation better compared to the words the and is. So in self-attention, compute which words are important for the translation. Before you continue on in this video, make sure you understand word embeddings. Otherwise, you will be completely lost. If you do not understand word embeddings, no worries. Earlier on in my AI and deep learning course, go to video 27 and we will go over word embeddings. Okay, so again, make sure you understand word embeddings and let's continue. Let's talk about what happens in basic self-attention. For each word embedding, do a dot product with every word embedding in the sequence to calculate the attention scores. So here, the word embedding is judge, and we do a dot product, which essentially measures similarity. So you could think of this instead of attention scores as similarity scores. So obviously, judge and judge will have the highest attention scores because they are the exact same word. And judge and fair are pretty similar. So it will have the second highest attention score of 3. And then Jamie and is are not as similar to the word judge. So the attention score or similarity score will be lower, 2 and 1. Normalize attention scores to get attention weights that sum up to 1. So here, softmax is used for normalization, and the order is still retained. What I mean by that is, well, judge and judge are still the most similar to each other because they are the exact same word, so it has the highest attention weight. Then judge and fair is in second place, so it will have the second highest attention weight of 0.24, and so on and so forth. Use attention weights to create word embeddings with context. So now this word embedding for judge has context that this means impartial and not an event, um, like a job fair or a county fair, etc. And of course, we don't just do this for the word judge. We also do it for Jamie, is, and fair. But there are some issues with basic self-attention. Word embeddings are weights that are optimized during training. And in this diagram so far, the only trainable weights are the word embeddings, which is inadequate. If we can give self-attention trainable weights, then this is something we can now optimize for. So remember that earlier on in the course, we talked about how this diagram is really important. Let's say we want a model that's really good at determining if this is a picture of a dog or a cat, or in this example, that's really good at translation. To do that, we want the best weights possible. So if we can give self-attention more weights to optimize, we'll have better outputs, hopefully. So how do we do that? Well, basic self-attention is using the same input 3 times. As you can see by my yellow ovals, there's 3 of them. And this can be referred to as the query, key, and value. So rather than this going on, for each word embedding, create query vectors, key vectors, and value vectors by multiplying with query weights, key weights, and value weights. So for the word embedding of judge, we multiply with the query weights, the key weights, and the value weights, to create query vectors, key vectors, and value vectors. Do a dot product of the first query vector with every key vector to get the attention scores. And again, you can think of the attention scores as like a similarity score, as we can see in this part of the diagram. Normalize attention scores to get attention weights that sum up to 1 in this part of the diagram. Use attention weights with the value vectors right here for creating context-aware word embeddings up here. Now, when I was first learning about attention and query, key, and value, this part, where everything you are reading here, was still a bit confusing and hard to understand for me. So to make things easier for you to understand, let's simplify things to ordering a pizza, where the query is like a toppings order. So I say I want salty and sweet. The key can be a description for an ingredient. So the key could be best peas, but the value or ingredient is actually just peas. Maybe the key is colorful bacon, but the value is just bacon. And lastly, the key could be frozen water, but the value / ingredient is actually just ice. So compare the query with the key to find the similarity. So for salty and sweet, pineapple is a really good match or similarity for sweet, so we give it 0.50. And then for the salty part, amazing ham and colorful bacon are matches as well, so 0.25 and 0.25. Use the similarity for the amount of value or ingredient used in the output. So here, the output is Hawaiian pizza, and we use 0.25 ham, 0.25 bacon, and 0.50 pineapple. So again, if everything you're reading here is still confusing for you, let's simplify it down to, well, ordering a pizza. Compare the query with the key to find the similarity, as we can see in this part of the diagram. Use the similarity for the amounts of value or ingredient used in the output. But rather than having an output of Hawaiian pizza, the output here is context-aware word embeddings. All right, that's it for this video. Thanks for watching.